Welcome to a new video. In this video we will discuss the eigenvalues and eigenvectors in the complex plane. In the previous example we have discussed the eigenvalues and the eigenvectors in the real plane or the real domain. So we will see how we can proceed if we have complex eigenvalues. Of course we will see the equation for the eigenvalue problem again, and we will see that step by step in our calculations, and we will verify these in MATLAB command window. Okay, we like to calculate the eigenvalues and the eigenvectors of this matrix, and we proceed as we have done in the previous example. So first the calculations, what we do is we start up with the eigenvalue equation, and this is the equation we need to solve or satisfy. We have the matrix A in this case. It must be multiplied by some vector, which is then scaled up in this form with the lambda, which is the scaling factor, and this lambda is our eigenvalue, and this vector v is the corresponding eigenvector. Okay, now in order to solve this, we can move this to the left side and also multiply that by the identity matrix, such that we have matrix minus matrix, so we stay in the same dimension. And we need to solve this. Of course, we put in the right side the zero vector in order to have the dimensions also correct. Now, in order to have the eigenvalue problem or the eigenvalue equation equated to zero, we need to have a dependent relationship, because that is now scaled up. That means our determinant must equal to zero. That is the condition. So you solve this equation. This is also where you can start in these kind of problems and questions. So we need to do the A minus the lambda I, which is then a new matrix, and for that we need to calculate the determinant. Now we see here in the matrix A 2, minus 5, 1 and 0. Now we know that the identity matrix has a 1, 1, 0, 0. So it means we only have here the lambda and there also lambda. Now we of course have a 0 here, so it's then 0 minus lambda, effectively minus lambda. The determinant of this one is the multiplication of this element with this element minus the product of these two. So that's actually shown here. So we see here 2 minus lambda times minus lambda minus 1 times the 0 minus 5, so that's actually effectively plus 5. Now when you work out the parentheses here, you get now here lambda squared minus 2 lambda plus 5. Now if you solve this, you will see what the eigenvalues are, and we will see always that we have, in this case, second order equation, so we will have 2 eigenvalues. Now we can try to factorize it, but that is not possible, so we need to solve it using the formula for second order equation. So we can say lambda 1 comma 2, so 1 over the 2 other is then minus the minus 2, which is actually this coefficient in front of this lambda, plus or minus the square root of the, again, this element or this coefficient minus 2 squared minus 4 times 1, which is the coefficient in front of the second order part, times 5, which is this final part, which is the constant, over 2 times the coefficient in front of the second order part. This is the general formula we use for quadratic equation. Okay, now when you solve this and you simplify this, this is now just 2. This is of course square root of 4 squared minus 20, and this is just 2. Now you can go on and you see that this is indeed minus 16. So we have a situation here which is undefined in the real plane or real domain. So we go in the complex domain. So we say the square root of the minus 16 will be square root of 16 times the imaginary value. So square root of 16 is 4. So we have then j times the 4, which is equivalent to minus the square root of minus 16. We can further simplify this because we have here 2 and a 4 and also a 2 in the denominator, so we can then move on to 1 plus or minus j2. Now you see here now the expression for the eigenvalues. So we can say our eigenvalues are, now let's number them, 1. Eigenvalue lambda 1 is 1 plus the j2, and the other one is lambda 2 is the 1 minus j2. And what you recognize here is then lambda 1 is the complex conjugate of the lambda 2. That means the following: you have here the plus and the reverse sign is here. So that's always the case where you have these eigenvalues in the complex plane. Okay, next step is about the eigenvectors. We start with the lambda 1. what we do is, as we have done in the previous example, we put that in an augmented matrix. So we have here this 0 vector again, and now we do specifically for the lambda 1. So the matrix A minus lambda 1 times the identity matrix. This will be then using the row reduction, the Gaussian elimination procedure, solved for the eigenvector for this eigenvalue. Let's substitute the value we have. So we have again 2 minus, now in this case specifically the lambda 1, minus 5 still, and here also 1, and this is now 0 minus lambda, which is then 0 minus lambda will be the minus lambda 1. We substitute here this value, so that's the next step. Now this is effectively here 1 minus j2, and this is minus 1 minus j2. So this is actually what we have, and the other two numbers are exact same. Now we need to solve this, so how do we proceed? So that was the problem in the previous example. We need to have here this row all 0, so we need to make this 0 and that 0. In order to make this 0, I need to have a value here which is a opposite sign of this one. So we can say, let's now multiply the second row by minus 1 plus j2, so the minus of this one. Only row 2, nothing more. So row 1 is just copied. Row 2 is here 1 times this minus 1 plus j2, and this one will be also multiplied by this. So we need to now work out the parentheses here. So it is minus 1 times minus 1 will be plus 1, minus 1 times j2, so it will be minus j2, and then we have here minus j2 times plus 1 will be then plus j2, and those two imaginary values will cancel each other out, and we have here minus j2 times plus j2. So now minus j times plus j is 1, so we have here actually 2 times 2, which is 4, and also the minus 1 times minus 1, so in total we have here plus 5. So that's effectively what we have. So this is now converted into this one. What you see is actually pretty nice that we have here an opposite sign of this one, and here is the opposite sign of that one. So we can now proceed with the next step, which is row 2 plus the row 1. So we add up for this row, that row. So the only change is in the row 2. Row 1 is just copied. This will be 0, of course, this is 0, this is 0. So that's exactly what we wanted. And now we see again that we have a free variable in the second column, which means this is the x2. And now we define that as, or set it equal to t, which is then an element of the real values in this case. Okay. Now then we have, looking at the first row, we can say 1 minus j2 times x1 minus 5 times x2 will be 0. So we need to solve this equation for x1. So we need to isolate x1. So we can say, let's put this to the right side. So 5x2 will be here, and divide this by 1 minus j2. So those are the two steps here. And I need to have an expression here which is convenient. So I use then the complex conjugate in the numerator and denominator. That's the next step. So we multiply the numerator by 1 plus j2. So the complex conjugate of this one, of course, also the denominator. Now we have here then 1 squared plus 2 squared in the denominator. This stays the same, but this is 5. So 1 squared plus 2 squared is 5, and this 5 is also, will cancel each other out. So we have only here, as can be seen here, 1 plus j2 times x2. And x2 was t, so we can also write it down like so. Now we can take this all together and then create this vector x, which will be then x1 and x2, where we have the x1 here and where we have the x2 here in terms of t. So we can substitute that, and we also have the t outside this vector. We have then for our eigenvector, for our first eigenvalue, we can say, if we now say that t is equal to 1, we can say that this is now the eigenvector. So for t is 1, we can of course pick another value for t except 0. Then our eigenvector is given by this v1. The nice thing about this is we don't have to do all the procedure here again for the lambda 2. We can say the eigenvector of the lambda 2 is the complex conjugate of the vector here for lambda 1. So V2 is the complex conjugate of the V1. That means we just have an opposite sign here for the imaginary values and we are done. This is actually pretty simple. Now we have everything. We have the eigenvalues and we have the eigenvectors. So let's proceed to the next step. That is in MATLAB, the verification of our calculation. This is the matrix we have given. You see here 2 minus 5 a semicolon 1 0. This is now the matrix. We here use the command to calculate the eigenvalues. And you see here the result. We see here 1 plus 2i, which is actually a j, and 1 minus 2i. So these are the two eigenvalues, and this is also what we had here. So this is indeed correct. Now let's also move on and check the eigenvectors. Now I defined here v1. You see here also the vector, so 1 plus 2i, and then here 1 in the second row. This is actually this. And for v2, I did in a similar form. Now I will multiply the matrix A with v1. I would like to see what is what's producing. I will do the same thing with A and v2. But this is of course an expression we cannot maybe see directly if this is correct or not, so we need to check this in more detail. So what I do is I apply again the eigenvalue equation. I substitute here the A, the matrix A, and also our eigenvalue v1, and I now multiply these matrix and the vector out. So I did 2 times 1 plus j2 plus minus 5 times 1. That will result in this. And the other one is 1 times the 1 plus j2 plus 0. And then I have this one. Now we can rewrite this. If I now take out 1 plus j2 out of this vector, I have this. So you can see that for yourself. If you do the calculation, 1 plus j2 times 1 plus j2 will produce actually this first row. Now I see here the lambda 1 and I see here the v1. So this is indeed the correct eigenvector for the corresponding eigenvalue. Now let's also check the final one, which is then the A times v2 in a similar form. So A times v2, you multiply this out, you get here the minus 3 minus j4 and then 1 minus j2. Now we put out this 1 minus j2. And now we need to have here 1 minus j2. So again, you can look for yourself that this is indeed correct. So 1 times 1 and 1 times minus j2 and then minus j2 times 1 and then minus j2 times minus j2. You will see that this is indeed the correct result. And now we have here again the lambda 2 and the v2, which is our vector to the second eigenvector. So that means both solutions for the eigenvectors are also correct. So we have verified our calculations using the MATLAB command window. Alright, this was our example considering the eigenvalues and eigenvectors for matrix where the eigenvalues and the eigenvectors are both in the complex plane. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video.